Hello and welcome. When performing simulations using ANSYS Fluent, once the numerical mesh is loaded and all the necessary physics models and boundary conditions have been defined, we need to select the numerical schemes and the solution controls which ANSYS Fluent Solver is going to use for solving the CFD problem. These options are contained in the Solution tab. In addition to selecting the numerical methods and solution controls, other options available in this tab can also help us impose convergence conditions by defining residuals and monitors, select the way in which the flow field is initialized, make the necessary final checks, and run the simulation. In this video, we will learn about the Solution Methods group of the Solution tab. More specifically, we will learn about the pressure-velocity coupling schemes and the spatial discretization methods used with the default ANSYS Fluent pressure-based solver. Let's get started. Here I have opened an ANSYS Fluent case file in which physics have already been set. Let us now directly go to the Solution tab, which is located between the User-Defined tab and the Results tab in the ribbon. The first group of the Solution tab is the Solution Methods group. Clicking on the Methods option opens the Solution Methods task page. The focus of this course will be the settings in this task page. ANSYS Fluent can simulate both compressible and incompressible fluid flows using two different solvers, the pressure-based solver and the density-based solver. For more details on specifics of these solvers, you can refer to the Lesson on Physics tab and also the ANSYS Fluent user guide. The Solution Methods task page looks very different for the two different solvers. As the pressure-based solver is the most commonly used flow solver and is the default option, in this lesson we will discuss the various options pertinent to the pressure-based solver. In the Solution Methods task page, we can specify the inputs for the pressure-velocity coupling schemes, flux types and different discretization methods for the convective terms of the flow equations. The default settings are recommended for most cases. If you have experimented with various settings and you would like to revert to the defaults, you can always do this by clicking here on Default. Let's now look at the different available options. Let's start with pressure-velocity coupling schemes. These coupling schemes control the manner in which the pressure and velocity fields are updated when the pressure-based solver is used. They can be either of the segregated type, that is, pressure and velocity are updated sequentially, such as simple, simple C and PISO, or coupled, where pressure and velocity are updated simultaneously. These four pressure-velocity coupling methods available in ANSYS Fluent can be selected from the drop-down menu here. The default option, that is coupled, is recommended for most steady-state flows. In general, segregated methods are faster per iteration, while the coupled algorithm usually requires fewer iterations to converge. As coupled is default and applicable to most simulation problems, let's discuss the coupled method further. Coupled can be used with or without the pseudo-time method option, which is a form of implicit under-relaxation and can be selected using this drop-down here further down in the task page. The default is to use them together, and the combination is often referred to as the pseudo-transient solver. Pseudo-transient is very robust for most of the routine applications, both compressible and incompressible. When we use the pseudo-transient solver, we will see an entry in the ribbon for a time scale factor, and it's useful to know what this does. In the pseudo-transient method, the Fluent solver advances the solution from one iteration to the next by using a false time step. After enough iterations, or false time steps, the solution will converge to a steady-state flow. The pseudo-time step size is determined automatically by the solver based on characteristics of the problem you are solving. Please refer to the last lesson of this course for more details on the impact of the timescale factor. You can also refer to the user and theory guides for more specific information about the method. Let's now discuss the inputs under spatial discretization. Here, we have options for the calculation of the gradients and the advection terms for all equations. Note that the equation names and the number of equations displayed here depend on the physics models chosen for the simulation. For example, if energy is unchecked, the energy equation option is not displayed under spatial discretization. Similarly, if a different turbulence model is used, variable names pertaining to that model are displayed. The default values are highly recommended, which are the least square cell-based method for the gradient, the second-ordered method for pressure, and the second-order upwind for all transport equations. One notable exception applies, though, to pressure discretization. Although second orders should be used for most cases for pressure, when solving a natural convection problem including gravity, second-order pressure could lead to unphysical results, and the pressure discretization must be changed to either presto or body force weighted. Going further down, for momentum and other equations such as turbulent kinetic energy, specific dissipation rate, and energy equation in our case, there are 4 different discretization methods that are available in ANSYS Fluent, which can be seen by clicking on any of the drop-down menus here. The second-order upwind is set by default for obtaining the most accurate solution on a suitably refined numerical mesh. The only reason that I would use the first-order scheme would be when a case is not converging to steady. In this case, I would first make sure that the mesh quality is acceptable and all my boundary conditions and physics are correct and consistent. After doing this, I would start the solution over doing some 50 to 100 iterations using first-order scheme and then continue the solution with the second-order upwind. Even for a ballpark estimate, I would move to first order only in case of convergence issues. For higher order estimates, quick and muscle schemes can be used. For a detailed discussion on the accuracy of these methods, please refer to the ANSYS Fluent Theory Guide. Other settings such as warped phase gradient correction, high order term relaxation are available to be used if and when required. These are advanced options and are beyond the scope of this lesson. Please refer to the user and theory guides to better understand the use case for these options. To summarize, in this lesson we discussed about the important parameters in the solution group of the Solution tab for the pressure-based steady-state solver. We discussed about the pressure-velocity coupling scheme and learned about the different methods that can be used, which are broadly classified into segregated and coupled approaches. We learned that for steady flow analysis, the most robust scheme is coupled with pseudo-time method turned on and set to global time step. Finally, we have also talked about the different interpolation schemes for other convection terms such as energy, momentum, etc. With this, we have come to the end of our video.